एंड इंडस्ट्रियल रिसर्च CSIR के 24वें स्थापना दिवस 84th फाउंडेशन डे प्रोग्राम के लिए एकत्रित हुए हैं। मैं डॉक्टर पारुल साहू, वरिष्ठ वैज्ञानिक SMC विभाग, इस कार्यक्रम का संचालन करने जा रही हूँ। ये हमारे लिए बड़े ही हर्ष की बात है कि प्रोफेसर LS शशिधर, निदेशक नेशनल सेंटर फॉर बायोलॉजिकल साइंसेज बेंगलुरु, मुख्य अतिथि के रूप में, एवं प्रोफेसर S रामकृष्णन, जो कि प्रोफेसर IISc बेंगलुरु से हैं, वे सम्मानित अतिथि के रूप में उपस्थित हैं। CSIR को विज्ञान एवं प्रौद्योगिकी मंत्रालय के अंतर्गत एक प्रमुख अनुसंधान एवं विकास संगठन के रूप में 26 सितंबर 1942 में स्थापित किया गया। CSIR 37 राष्ट्रीय प्रयोगशालाओं, 39 आउटरीच केंद्रों, एक नवाचार परिसर, अखिल भारतीय उपस्थिति वाली 3 इकाइयों का एक गतिशील नेटवर्क है। CSIR समुद्र विज्ञान, भूभौतिकी, रसायन, दवा, जीनोमिक्स और जैव प्रौद्योगिकी से लेकर खनन, वैमानिकी, इंस्ट्रूमेंटेशन, पर्यावरण अभियांत्रिकी और सूचना प्रौद्योगिकी तक विज्ञान और प्रौद्योगिकी के व्यापक स्पेक्ट्रम को कवर करता है। 10 अप्रैल 1954 में स्थापित केंद्रीय नमक व समुद्री रसायन अनुसंधान संस्थान, सेंट्रल सॉल्ट एंड मरीन केमिकल रिसर्च इंस्टीट्यूट, CSIR की प्रयोगशालाओं में से एक है। CSIR CSMCRI वर्तमान में विविध और अत्यधिक अनुप्रयुक्त अनुसंधान क्षेत्रों जैसे नमक और समुद्री रसायन, जल विलवणीकरण, मेम्ब्रेन आधारित जल शोधन प्रक्रियाएं, सूक्ष्म और विशिष्ट रसायन, अकार्बनिक पदार्थ एवं उत्प्रेरण, नवीकरणीय ऊर्जा, समुद्री शैवाल एवं सूक्ष्म शैवाल, पादप आणविक जीव विज्ञान, जीव प्रौद्योगिकी, अपशिष्ट प्रबंधन और प्रभाव मूल्यांकन, समुद्री पर्यावरणीय अध्ययन आदि विषयों पर केंद्रित है। भारत में वैज्ञानिक अनुसंधान और औद्योगिक विकास में CSIR के महत्वपूर्ण योगदान का सम्मान करते हुए हम प्रत्येक वर्ष स्थापना दिवस समारोह मनाते हैं। इस संक्षिप्त प्रस्तावना के साथ मैं आज के अतिथियों प्रोफेसर LS शशिधर एवं प्रोफेसर S रामकृष्णन का स्वागत एवं अभिनंदन करती हूँ। अब मैं स्थापना दिवस समारोह के मुख्य समन्वयक डॉक्टर विश्वजीत गांगुली से हमारे दोनों अतिथियों और साथ ही साथ हमारे निदेशक महोदय डॉक्टर कनन श्रीनिवासन एवं प्रशासन नियंत्रक श्री विरंची सारंग जी को मंच पर लाने का आग्रह करती हूँ। हमारी परिषद का अपना आदर्श वाक्य है और यह इसके CSIR गान में परिलक्षित होता है। CSIR स्थापना दिवस समारोह में CSIR गान की प्रस्तुति की जा रही है। गान के दौरान आप अपने स्थान पर ही बैठे रहिए। अब हम अपने अतिथियों के सम्मान का कार्यक्रम शुरू करेंगे। तो मैं निदेशक महोदय से निवेदन करती हूँ कि वे हमारे मुख्य अतिथि महोदय प्रोफेसर LS शशिधर जी को फूलों के गुलदस्ते से उनका स्वागत एवं अभिनंदन करें। मैं निदेशक महोदय से पुनः अनुरोध करती हूँ कि वे हमारे सम्मानित अतिथि प्रोफेसर S रामकृष्णन का फूलों के गुलदस्ते से स्वागत एवं अभिनंदन करें। धन्यवाद। कार्यक्रम को आगे बढ़ाते हुए मैं स्थापना दिवस समारोह के मुख्य समन्वयक डॉक्टर विश्वजीत गांगुली को स्वागत संबोधन के लिए आमंत्रित करती हूँ।
Namaskar and good afternoon. Chief guest of today's function, Professor LS Shashidhara, National Center for Biological Sciences, Bangalore, Director. Today's guest of honor, Professor S. Ramakrishnan, Department of Inorganic Physical Chemistry, Indian Institute of Science, Bangalore. Dr. Kannan Srinivasan, Director, CSIR, CSMCRI. Controller of Administration, Mr. Biranchi Sarang. Dr. Parul, former and present colleagues of CSMCRI, distinguished guests, colleagues of CSIR labs, students, on behalf of CSIR, CSMCRI family, I extend a warm welcome to all of you for joining us today to celebrate the 84th Foundation Day of Council of Scientific and Industrial Research. We celebrate the CSIR Foundation Day on 26th of September in the Institute, but the grand celebrations of 84th Foundation Day has taken place in the august presence of Honorable Vice President of CSIR at New Delhi on 26th of September, and we are celebrating this event today. A very warm welcome to Professor Shashidhara and Professor Ramakrishnan for generously accepting our request to grace this occasion. CSIR has completed more than 8 decades of journey and demonstrated the capability to strengthen the country in scientific, social, strategic, and economic fronts, and now CSIR is planning to contribute to position India as a developed nation in the global arena and the mission of Viksit Bharat 2047. CSIR CSMCRI is one of the constituent labs of CSIR, works on salt and marine chemicals, and the only institution in the country works on salt research, and started with the goal to make the country self-reliant in salt producing. I'm happy to share that CSIR CSMCI is geared up to contribute in the area of salt and marine chemicals, water technology, seaweed mission, and to the leaders in such fronts in the mission of Viksit Bharat 2047. CSMCI is making a commendable progress and soon propel India into a top salt producing and major seaweed producing and processing nation in the future. I just would like to quote that seaweed farming and its application in one of the 10 commitments by CSIR for Viksit Bharat 2047. With these words, I once again thank our chief guest and guest of honor for accepting our invitation with great promptness and be here with us in spite of their very busy schedule. On behalf of CSIR CSMCRI family, I once again welcome our guests and all dignitaries on the dais, and connected through the visual platform into this function. Thank you.
धन्यवाद डॉक्टर गांगुली। अब हम अपने मुख्य अतिथियों का एक एक करके वक्तव्य की ओर बढ़ेंगे। उससे पहले मैं सभी मंचासीनों से निवेदन करूंगी कि वे कृपया सामने की ओर बैठ जाएं। मैं समारोह के सम्मानित अतिथि एवं प्रथम वक्ता प्रोफेसर S रामकृष्णन का परिचय प्रस्तुत करना चाहूँगी। प्रोफेसर रामकृष्णन एक पॉलीमर केमिस्ट हैं जो आईआईएससी बेंगलुरु के इनऑर्गेनिक एवं फिजिकल केमिस्ट्री विभाग में लगभग 37 वर्षों से कार्यरत हैं। उन्होंने 1980 में यूनिवर्सिटी ऑफ मुंबई से बीएससी एवं 1982 में आईआईटी बॉम्बे से एमएससी डिग्री प्राप्त की। 1988 में उन्होंने यूनिवर्सिटी ऑफ मैसाचुसेट्स एमहर्स्ट से पीएचडी की उपाधि प्राप्त की। 1988 से 90 के दौरान उन्होंने न्यू जर्सी के एक्सॉन रिसर्च एंड इंजीनियरिंग कंपनी कॉरपोरेट रिसर्च प्रयोगशाला में पोस्ट डॉक्टरल अध्ययन किया। उसके बाद उन्होंने आईआईएससी बेंगलुरु के इनऑर्गेनिक एवं फिजिकल केमिस्ट्री विभाग में फैकल्टी पोजीशन पर ज्वाइन किया, जहां 2010 से 2016 वे डिविजनल चेयर भी रहे। वे 2016 से 2018 तक आईआईएससी के उपनिदेशक भी रहे। प्रोफेसर रामकृष्णन डिज़ाइन एंड सिंथेसिस ऑफ कंट्रोल्ड पॉलीमर स्ट्रक्चर पर अपने अध्ययन के लिए जाने जाते हैं और इंडियन एकेडमी ऑफ साइंसेज के एक निर्वाचित फेलो हैं। काउंसिल ऑफ साइंटिफिक एंड इंडस्ट्रियल रिसर्च ने रासायनिक विज्ञान में उनके विशिष्ट योगदान के लिए 2005 में विज्ञान और प्रौद्योगिकी के लिए शांति स्वरूप भटनागर पुरस्कार से सम्मानित किया। वे 2011 से 2021 तक जेसी बोस फेलो भी रहे। प्रोफेसर रामकृष्णन का रिसर्च ग्रुप प्रमुखतः न्यू सिंथेटिक रूट डेवलपमेंट, नोवेल पॉलीमराइजेशन मेथड डिज़ाइन एवं डेवलपमेंट, रिएक्टिव कोटिंग्स एवं मॉलिकुलरली डिज़ाइन पॉलीमेरिक मटेरियल्स पर शोधरत है। इस संक्षिप्त परिचय के साथ अब मैं प्रोफेसर एस रामकृष्णन को उनके विशिष्ट व्याख्यान के लिए आमंत्रित करती हूँ। व्याख्यान का शीर्षक है प्लास्टिक्स अ बून टर्निंग अ बने।
धन्यवाद. That's the Hindi that I will use, and उसके बाद काफ़ी मुश्किल है, so. But fortunately, I went to a Kendriya Vidyalaya, and therefore I know Hindi reasonably well, adequately enough to understand. But my ability to converse in Hindi is only limited. So. ये क्या है? Which is laser pointer? This one. Okay. Okay, and this is so. Okay. Oh. Okay. Oops. I think I've gone. I'll just go to the first one. So I was when Dr. Kannan invited me, I was very pleased to be here because I've never visited Bhavnagar. I've been told so much about this lab by my colleague, Professor Krishnan, who used to be in the council and also was a chair, I think, at some point. So I'm really delighted to be here and be with you and try and talk about it. So he told me that I should give a talk on a general topic. I'm not so good at giving a talk at a general topic, and I'm looking forward to Shashidhara's talk because it's really much more general than what I have in mind. So when he told me, I said, okay, what shall I talk about? I've been interested in this topic, and I've given some lectures more to a general public in school and so on this topic. This concerns something that we all worry about a lot as a human society, right? So is plastics a boon or a bane? I actually had, is it a boon turning a bane? In other words, was it a boon at one point and now we are worried about the consequences of plastics that we have produced and continuing to produce? I had a nice video clip that I wanted to play, but can you play that? And so this was a clip from I think the front row people will recognize this.
He's just I look at him and I can't believe it. I simply can't believe it.
I just want to say one word to you. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
Exactly how do you mean?
There's a great future in plastics.
Okay.
Think about it.
So this is
What do
from
you
an
think
old
about it?
movie. Some of you might have seen it. That gentleman there who is looking young is Dustin Hoffman. He was young. It's a 1967 movie. It was taken in 1967. And this movie, at that time, plastics was emerging as a very important material for development in the future, and I'll show you something. So it was clearly a boon at that point, right? And so now we are, you can go ahead and change it, yeah. So the question that I'd like to pose today really is, I'm going to go quickly with that. So what comes to our mind? I mean, this is of course a collage of lots of different items that have been made from plastic. It's colorful, attractive, easy to form and so on, right? A variety of plastics, I'll tell you a little bit. Or is it this? And to most of us today, it is actually this that comes to our mind when we think about plastics. The enormous amount of pollution that has been caused by it. इसमें ये नहीं है ना? Oh, है अच्छा. Oh, okay. Upper one, okay. Yeah, so it's this kind of generation of large amount of plastic waste both in ocean as well as in the landfills. So the question really is that, I mean, does this really mean like the clamor that we have today of banning use of plastics altogether? Is that something that makes sense? I mean, that's a question that we'd like to ask. You know, what is it that we do in order to continue to need to use plastics? And the answer to that is fairly obvious, that we can't ban the use of plastics altogether, okay, because there are lots of environmental positives of plastic which I'll tell you a little bit about later. So what are some of the most common plastics? If these three, polypropylene, high density polyethylene and polyethylene, just these three class of polymers, these pure polymers itself compose about 60% of the total plastics that we produced. Okay, so just three polymers, and all three of them are pure hydrocarbon. Okay, they have no other element other than hydrogen and carbon. So really, in some sense, you might consider it as borrowed fuel. You know, that means you've taken it out, a petroleum resource that you've temporarily used as a plastic, and then if you burn it, per unit gram, you get the same calorific value as that of petrol or diesel. Okay, so exactly the same. So in some sense, this can be reutilized as fuel, but with the problems that it comes with. And of course, you have polyvinyl chloride, polyethylene terephthalate. This is among these, polyvinyl chloride and PET are the only ones that have elements other than carbon and hydrogen. Okay, and some of the uses that have shown there are examples of the plastic. So fundamentally, what is it that, as a chemist, what is it that makes polymers such an attractive material for use? Okay, so the obviously it is one of the, as I see it, it's one of the very interesting molecular materials. It is, when I say molecular materials, the material itself is constituted of independent molecules, although large molecules. They are constituted of independent molecules, each of which in principle have the translational degrees of freedom. Okay, so it's a collection of molecules that form the material, and because it's a collection of molecules, it exhibits several interesting properties such as elasticity. There is very little, there is almost no material that is known that can deform to such extents elastically. That means it goes back to its original dimension when you let go the force, right? So rubber is uniquely a property of long molecules, polymers. It's lightweight, strength, processability, viscoelasticity, and so on. Numerous properties that make it attractive. And as I said, you know, polymer chains are very long molecules. Okay, so if you stretch out a molecule of polyethylene from one end to the other in a straight line, it will be about a micron in length. Okay, so that's the length of the molecule. But of course, polymer chains have a way to sort of adopt a random coil, and the dimensions become much smaller. So the sphere that encapsulates this entire chain is only about 30 nanometers or so. It's much smaller than the stretched out chain. Okay, and it's because of this that it has its unique properties. Two very important characteristics of polymers that make it very useful. One, molecularly, it is entangled. In other words, even though they are a collection of individual chains, they don't have, typically in a melt state, they don't have independent translational degrees of freedom. And the reason for that is polymer chains are entangled. Entangling is like a knot. It's like a knot that you have in a bundle of thread. And this entanglement acts as a physical crosslink that prevents the motion. And the fundamental reason why polymers have the strength that they do is because of this particular feature of polymer chains. Of course, the segments that lie between these entanglements can sort of wiggle and jiggle or sort of have motion, and the temperature above which it has enough energy to move is actually very often referred to as the glass transition temperature. In other words, that is in some sense the temperature beyond which the material, most polymeric materials cannot be used. That is, a physical use temperature is defined by the glass transition temperature for many polymers. And another unique feature of polymers are really the fact that a polymeric material is not only structurally heterogeneous, they are also macroscopically heterogeneous. When I say macroscopically heterogeneous, all regions of that polymeric material are not identical, okay? They are heterogeneous. And the origins for the heterogeneity is the fact that they are only partially crystalline. If you take an object like this, and you expand it, you will see that there are spherulites, and each spherulite is a bundle of crystals, and between the crystalline domains invariably there will be some amount of amorphous domain, and if you expand the amorphous domain, it is really a collection of chains that are disordered. Okay? And this composite nature is very important for the properties that polymers exhibit. Okay? So, these are the two features that I would like you, and of course, crystalline domains resemble a sort of uncooked spaghetti, and of course, once you cook it, the material that you get resembles the amorphous domains. And both these actually have very important properties that enable the composite behavior of a polymeric system. So, as I mentioned, why is it become indispensable in our life? Because of course, it is lightweight, easily processable, you can make a lot of different aesthetically pleasing materials that provide you a lot of convenience, right? And what is the good? So, I told you that polymers have environmental positives, and what are they? They are far lighter and they are much easier to process. Okay? These are two things. So, imagine the days when we had to transport water, potable water, drinking water in glass bottles. The weight of the bottle compared to the weight of water that you are carrying is a very significant fraction, sometimes higher than the weight of the water that you are carrying. Unlike what we do today, and most of the lightweight containers reduce the energy consumption during transportation. And of course, the most important part is the amount of energy that is consumed for manufacturing products out of plastics. So, the lower processing temperature, typically most plastics are processed at temperatures far below 300 degrees, polyethylene and polypropylene are even below 200 degrees, right, and hence the energy consumption is far smaller than processing metals or ceramics in general. That is clearly something that leads to an environmental positive, correct. And what is the bad? That is the environmental negatives. It is the fact that as of today, majority of the polymers are produced, the starting material is not a sustainable resource, which means it is petroleum. The only saving grace is a very small fraction of the petroleum that we mine is actually utilized for making plastic. Majority of it goes into energy generation, right, like gas and so on. So, which means in principle, if we find alternate sources of energy, which we will certainly, we will not have as much of an issue as this. And the second one is the pollution that plastics are causing both in air, water and soil. Okay? And today we are aware of the fact that this is appearing to be a menace that we still do not know the consequences of. In other words, extremely tiny particles of plastic that appear to get into the food chain and then eventually into the bodies, into our bodies. We are not quite sure what the implications of that is on the health of our livestock and ourselves. So, what have people done? Okay, so degradable versus non-degradable, we clearly understand that what needs to degrade are only the ones that are discarded. Okay, so the rest of it we do not want it to degrade, we would like it to be used as long as we can and probably recycled, as I will tell you. So, discarded waste are packaging, disposable plastic cutlery, flushable toilets, trash bags, etc., right. All of this we would like these materials to be designed so that even if we discard them, they should actually degrade into benign products, okay, and that is important to remember. Now, the global plastic production, sorry about the slide, has gone up from something like 1.5 million metric tons to something like 380 million metric tons in the last 70 years. And the fraction of and the cumulative plastic production, that is the total amount of plastics that we have produced as of 2015 from this source that I picked up, is about 8.3 billion tons of plastics that we have produced cumulatively altogether in these several years, of which 6.3, that is almost 75% of this, is actually being discarded, already discarded. So, this is something that past generations have already thrown away, okay? And only 9% of the total amount that we have generated has been recycled. So, that is a really pitiful statistics, okay? When you think about it, it is a really pitiful statistic. And as I mentioned, the types of plastics, majority of it is hydrocarbon, just polypropylene, polyethylene and two types of polyethylene compose about 50% of it. And the usage, this is what is important. Again, sorry about the slide, I wasn't expecting it won't be readable. About 40% of the plastic that we generate or we produce is used for packaging. Okay, that's a huge amount, and that's the one that is getting into our waste cycle very rapidly, because the life cycle time for packaging is much smaller than most of the other life cycles, right. So, if you have a bucket, you would use it for a decade maybe and so on. So, the time of usage of other articles are much longer than the ones from packaging. So, it is the remarkable convenience that attracted us to the use of plastic, and it is the incredible short-sightedness of humans that has brought us to this brink where we are now sitting and worrying about all the plastic that we have generated. So, now I will come to a little bit of the technical part of the talk just for the next 5-7 minutes to tell you what have people been looking at as strategies for utilizing and sort of evolving a process that would be more benign and sustainable. I would refer to people who are interested in this topic to this really beautiful article in Nature that came a few years ago, which sort of comprehensively provides this view on what and how to address this. So, most plastics are actually mechanically easily recyclable, because majority of the material that I spoke about are thermoplastic, which means you can melt it like you can melt wax and reprocess it into any other product. Okay, so, that in principle mechanical recycling is something that you can take a used plastic, simply melt it, it becomes individual chains, and you cool it down, it becomes the product that you want. Sounds simple, but it is obviously not as simple as that. A majority of the plastics have, you can take the plastic material and you can thermally recycle it. That means you can break it down like you're cracking petroleum into low molecular weight products and use it as fuel or wax. You can burn it to get energy, as I mentioned, or you can leave it in landfills, which is what we have done majority of the cycle. So, what are the issues, challenges with the mechanical recycling? One is that most plastic items that we have are not a single pristine item. Okay. They have many other components that have been added to prevent degradation. Okay. That means stabilizers, colorants, pigments and so on. Okay. And so, it makes it hard for you to mechanically recycle because of the thermal stability of the added components that are present. The second and very important property is that once you recycle, the material properties, let us say the mechanical strength of the material is not the same as it was in the virgin plastic. Okay. So, that means each time you recycle, the property actually depletes, and that is a serious issue for recycling. And the last one is of course the economic competitiveness. That means how does the price of a recycled plastic compare with that of the virgin plastic, considering the fact that there is cost for retrieval, cost for reprocessing, etc. So, if it is not competitive, then and if the material property is degraded, it is not a viable solution, right. So, that is the worry that we have with that. Now, what are the challenges with chemical recycling? Chemical recycling is a process where you take the plastic material and convert it back to the monomer. That means you transform it back to the monomer and then you repolymerize. In such cases, you get essentially the same quality plastic that you had with the virgin plastic. Okay? But that has the challenges, and that is effective transformation strategies that will allow it to be done in an economically viable fashion is yet to be discovered, okay, in most cases, except probably polyethylene. And the last one is a very interesting thing that has become much more relevant in today's context, and that is called upcycling. In other words, you take a material and don't tolerate depletion in property, but try and see whether you can make something whose property is better, but not of the same material, but maybe of a different material. Okay? And I will give you one or two examples before I close. In other words, upcycling is basically something that improves the property of the outcome than the starting material. So, essentially the challenges in upcycling are the following. Firstly, it is to view plastic. This is a very important idea. Plastic is a purely organic compound, organic material, most plastics, right? Just as petroleum. So, can you view it as a source of chemicals or source of polymers? Can you use it as a source? Okay, so, as a resource, just as you are using petroleum, can wasted plastic be used as a resource for organic matter and develop processes to convert it to improved materials or improved chemicals or chemicals that you can use for other purposes. And you have to do so. These are three critical criteria. You have to do so with economic competitiveness, do so keeping in view of recyclability. In other words, whatever you do in the process, can that process be recycled? Can it be repeated using used plastic? Okay, so that's the second part. And so, and do it keeping in these two points in mind is the key challenge. I'll just give you two examples of this, and I will sort of move to the end. One is PET. PET, by the way, is probably the most effectively recycled of all the plastic components that we have, okay, today. In India, in fact, it's one of the largest across the world. We recycle probably close to 80% of the PET. Mechanical recycling being one of the very foremost procedures for this. But here is an example where the authors have used a bio-derived derivative like these two monomers and transformed this to a cross-linked network. Okay, and they have figured out that this material that you generate, this polyester, which is an unsaturated polyester, can be very effectively used for making fiber reinforced plastics. Okay, traditionally unsaturated polyesters are made from maleic anhydride and glycols, but you can use used PET to manufacture FRP, and the mechanical and thermal properties are comparable or even better than the original FRP itself. So, clearly the positives are biosourced and the economic viability is there. Only thing is, this is a process that is a multi-step process, which is the red in this idea. You can also use similarly polycarbonates and insert other diols to make polycarbonates with two kinds of repeat units by integrating it with biosourced molecules to make it viable. Okay. Polyethylene, there have been many efforts, and one of the interesting ones, I will show you one more before I close, and this is to use a catalyst, and it's here is where catalysis is very important. In other words, how do you take a hydrocarbon that is generally believed to be fairly inert and insert heteroatoms either within it or in the pendant? And here they have used a ruthenium based catalyst to insert oxygen atoms onto polyethylene. And this transformation of low density polyethylene to this material has been fairly effective in generating coatings using recycled plastic material. So, in other words, I will this is useful chemicals. This is generating dicarboxylic acid from polyethylene, basically breaking it at different points to generate dicarboxylic acid under an oxidative condition, and then transform them to polyesters. Okay, so that's the idea. This I will skip. It's okay. This is a matter of. So, what is the origin for this depletion of properties when you recycle? When you recycle thermoplastics are heated and they experienced enormous amount of shear forces when they are processed. Okay, whenever you process a molten plastic which is highly viscous melt and you shear it, you are applying enormous amount of force, and that kind of force in the presence of entanglement can lead to chain scission. Okay, that means the chains can break, and as a result long polymer chains which attributes its properties to the length of the polymer chain break into smaller pieces. As a result, the properties of the polymers deplete. Okay, so this is something that is intrinsic to this. So the idea is, how do you recycle plastic without losing these properties? And I'll just give you one very creative example that came a couple of years ago. It was a paper that was published in Science, again uses a catalytic process to insert an amide linkage on the polyethylene backbone. That is, you take a hydrocarbon and insert an amide. It's a pendant amide. So the NHCO phenyl is actually comes as a pendant unit on this, and here they explain the process that leads to this this catalytic transformation. And once you insert an amide, the difference between polyethylene and nylon, for instance, is just the presence of an amide, and that transforms the properties remarkably, right. So the idea that you can take polyethylene and insert amides, linkages, not linkages in the backbone but pendant units, is adequate to improve the recyclability. And what the authors show in this is fairly interesting, and that is, if you take a polymer that is recycled polymer, you will immediately see that there is a tremendous depletion of mechanical strength as well as the elongation at break. That means how much can you stretch before the material breaks. Okay, so that both these properties deplete with each cycle of polyethylene. But once you transform the polyethylene and insert a certain amount of the amide, and you look at this here, for those of you who can see it, it is only a few percent. This is 1% and 2% incorporation of amide into the polyethylene, and that is adequate to change the extendability by almost 10 times. This is about it extends to 200%, and this is about 1070%. In other words, the extensibility is enormously improved by just simply inserting a small percentage of these amides. Okay, so that means the power of the hydrogen bond in these materials, which is completely absent in polyethylene, reveals this idea. Now, before I close, I just want to sort of have you ponder some thoughts. I had some other slides, but I summarized it in this text, and that is, you know, any production, our lifestyles today has led us to utilize huge amounts of synthetic materials. When I say synthetic materials, I do not mean materials alone, but synthetic systems, drugs, all kinds of molecular systems that have not existed naturally. Okay, so we have produced a large amount of synthetic substances, including small molecule chemicals, polymers, etc. Okay, and much of the synthetic material generation requires utilization of energy. Okay, and I call it synthetic energy because majority of our energy that we have generated so far is coming from coal, essentially burning thermal power plants, burning coal. So we have used mostly synthetic energy to generate synthetic materials, and so this process of synthetic production, that means whether it is energy or systems or materials or compounds or chemicals, has obviously led to enormous amounts of aerial pollution, right, both material and aerial pollution. Plastics is an example of material pollution, and of course this is an example of carbon dioxide and other emitted gases are an example of aerial pollution that happens as a result of generating synthetic energy. So the point is, our efforts now should focus on developing new chemistry which is not only benign to view and utilize waste as a useful starting material for production of sustainable production in a sustainable cycle. In other words, chemistry has to be generated or discovered that will utilize waste that we have, all kinds of organic matter. I mean, your lab is a wonderful example of utilizing organic matter from seaweed for generating a variety of products, right. So everything as far as the chemist is concerned is a source of organic material. So is the enormous amount of plastic waste that we have. So how do we discover new chemistry to be able to transform this to useful starting materials that we can then produce in a benign way? So in some sense, being from here, So I can't stop without saying this. It is clear that being from this state and close to where Gandhiji was born, it is probably the most befitting statement in today's context, and that is, there is enough for everybody's need but not enough for everybody's greed. Clearly that is something that we have to learn to conserve, to reuse, and to re-examine the way we are living and re-examine the way we are going to discover science for the benefit of creation of products. So with that, I'd like to stop, and thank you for the attention.
धन्यवाद प्रोफेसर रामकृष्णन, आप आपके व्याख्यान द्वारा प्लास्टिक, पॉलीमर केमिस्ट्री, उनकी विशेष प्रॉपर्टीज़, प्लास्टिक के अच्छे बुरे पर्यावरणीय प्रभाव, प्लास्टिक रिसाइकलिंग और उससे भी आगे प्लास्टिक अपसाइकलिंग के विषय में अपना ज्ञान साझा करने के लिए आपका विनम्र धन्यवाद। मैं निदेशक महोदय से अनुरोध करूंगी कि वे हमारे वक्ता प्रोफेसर एस रामकृष्णन को एक स्मृति चिन्ह आभार प्रदान करें। धन्यवाद। अब स्थापना दिवस व्याख्यान के लिए हमारे मुख्य अतिथि एवं विशिष्ट वक्ता प्रोफेसर एल.एस. शशिधर को बुलाने से पहले मैं उनका संक्षिप्त परिचय प्रस्तुत करना चाहूँगी। प्रोफेसर शशिधर नेशनल सेंटर फॉर बायोलॉजिकल साइंसेज बेंगलुरु के निदेशक हैं। उन्होंने अंडर ग्रेजुएट एवं पोस्ट ग्रेजुएट शिक्षा यूनिवर्सिटी ऑफ एग्रीकल्चरल साइंसेज धारवाड़ से प्राप्त की। उन्होंने यूनिवर्सिटी ऑफ कैम्ब्रिज यूके से पीएचडी की उपाधि प्राप्त की। प्रोफेसर शशिधर जेनेटिक्स, मॉलिकुलर बायोलॉजी और इवोल्यूशनरी बायोलॉजी में विशेषज्ञता रखते हैं। उनके समूह ने ड्रोसोफिला को एक मॉडल सिस्टम के रूप में उपयोग करते हुए एम्ब्रियोनिक डेवलपमेंट के दौरान ऑर्गन डेवलपमेंट को निर्धारित करने और ग्रोथ कंट्रोल को रेगुलेट करने वाले प्रमुख मैकेनिज्म की पहचान की है। उनकी बेसिक एवं अप्लाइड बायोलॉजी शोध उपलब्धियों के लिए प्रोफेसर शशिधर को अनेक प्रतिष्ठित पुरस्कारों जैसे CSIR के टेक्नोलॉजी प्राइज़ इन बायोलॉजिकल साइंसेज, शांति स्वरूप भटनागर पुरस्कार एवं JC बोस नेशनल रिसर्च फेलोशिप से सम्मानित किया गया है। वे तीनों राष्ट्रीय विज्ञान अकादमियों, नेशनल एकेडमी ऑफ साइंस इंडिया, द इंडियन नेशनल एकेडमी ऑफ इंजीनियरिंग एवं द इंडियन एकेडमी ऑफ साइंसेज के सदस्य हैं। प्रोफेसर शशिधर भारतीय विज्ञान शिक्षा एवं अनुसंधान संस्थान आईसिर पुणे और अशोका विश्वविद्यालय के संस्थापक सदस्यों में से हैं और उन्होंने इनके विकास में महत्वपूर्ण योगदान दिया है। इस संक्षिप्त परिचय के साथ अब मैं प्रोफेसर शशिधर को स्थापना दिवस व्याख्यान फाउंडेशन डे लेक्चर के लिए आमंत्रित करती हूँ। व्याख्यान का शीर्षक है पोस्ट इंडिपेंडेंट इंडियन साइंस, लेस नोन स्टोरीज, अनइमेजिनेबल इम्पैक्ट। सर, आपका स्वागत है।
Thank you very much for kind invitation, Professor Kannan, and all the members of Central Salt and Marine Research Institution here. This is my first visit. I'm really already impressed. I'm so impressed and I'm so excited to talk about the marine ecosystem on which you're working. It started as a salt and chemical research institution. I think it's the salt and chemicals, as you also keep saying, most of them are derived from the large ecosystem, and that is the marine ecosystem. That marine ecosystem also has lots of organisms which are also adding value to the chemicals which otherwise can exist without living systems. But the value addition that's coming from living organisms is what you are also studying and exploiting, and for the cause of humanity. And it's congratulations on the Foundation Day. In fact, I'm also a CSIR person. In fact, I grew up. My first professional journey was at a CSIR institution, a Center for Cellular and Molecular Biology, for first 17 years of my life. and where I started working in the area of developmental biology. Because the CSIR institution, we also do applied and translational research. That's where I started thinking about how to apply whatever we do in for societal application. One of them was in the context of drug discovery, cancer biology, and so forth. So I started as a plant biologist to animal biologist to more translational cancer biologist now. Clinical research is all because of CSIR institution. It's the influence. And today my talk is a history talk in a way, but a history of science and history of science and technology of independent India, post-independence, 1947 onwards. Where we were and where we are now is actually a story of science and technology. It is true for all over the world. The entire 20th century, if you look at it, whether it is genocides or wars or but the growth, development, increase in the lifespan, healthy aging, healthy living, everything is related to science and technology. So the science and technology are two different things. Science, I'll come to that in a minute. Science is all about discovering the knowledge about our world, the surrounding world, as well as human world. Human world includes our body and also our social interaction. The second part is, of course, the application of that knowledge, where it comes, technology will come into picture, right? Yeah. This is the one, right? Yeah. So for this, audience, I don't have to talk about science, but just really I want to mention one part, because there may be students here. Science is not that physics, chemistry, math and biology that you study in your textbook. It is the way we discover knowledge, new knowledge, the way we understand the world. The method that basically goes in behind that is actually the science, right? It's all called scientific methods. It's evidence based, hypothesis driven. You generate evidence, you validate your hypothesis. Invariably, you falsify the hypothesis rather than try to prove something. And in the process, you understand the world. And you understand the world beyond human sensory perception. When I say beyond human sensory perception, it's not one or two humans. For example, all the 7 billion people who are living on Earth, one by one, you ask them, what do you see in the sky every day? They will say every day they will see sun moving from east to west. But the reality is a completely opposite, right? We don't even experience this. So can you discover something we don't see, we don't experience, and none of us have seen, none of us have experienced. That's the beauty of science, because the method that we use is totally unbiased, is not human sensory organ specific, right? And that's how the science has grown over the years, and particularly in the last 150 years has enabled our better understanding of both biological world and non-biological world, from atoms to galaxies to from simplest living organism like bacteria to humans, right? It progresses by observational and pre-designed studies. As I told you, science and technology are two different things. Technology can happen even in the absence of science. For example, agriculture started, or invention of the wheel, building buildings, all of these things were happening even without knowing the mechanics, without knowing anything about the science behind those technology. But the understanding of the science accelerates technology. That is exactly what you people are doing. Today, since morning I was talking about, everybody talks about the fundamentals of the biology, at least the part I understood, and I'm sure Ramakrishnan was talking about the chemistry part of it. And you first explained the fundamentals of what biology is driving, let's say seaweed, metabolites, or seaweed, very different proteins that are expressed. Why do they grow at such high concentration of salt and kind of everything? And then you try to exploit. That's basically technology, right? At the same time, technology helps science too. All of us have benefited microscopes and telescopes and spectroscopes and all kinds of things to make new discoveries, without which we would not have seen the world which actually exists beyond human perception. And conversion of knowledge to technology or knowledge to societal application was a slow process, right? For example, as a biologist, I normally give this as an example. Darwin published his work on evolution in 1859. For about 50 years, no one understood or not was even accepted. And then by beginning of 20th century, people realized that it is true and there is sufficient evidence for this. And people also started looking at similarities across different organisms. Although chemistry of life was not known at that time, DNA was not discovered, we didn't know anything about genes, but still people realized that the physiological level, there is a lot of similarity. One of them is actually how to control glucose levels in our blood. It's a physiological process, right? And that is similar amongst all mammals. In 15s and 20s, when proteins were discovered, one of the earliest protein to discover and characterize was insulin, which is required for glucose metabolism, controlling the glucose metabolism in our blood. And people also found out that the insulin at the biochemical level, when you do work in the lab, whether you extract from a cattle or extract from a human or from pigs or from horses, they function exactly similar way. That realization immediately made insulin extracted from the animals as a therapy for diabetic patients, right? At least the type 1 diabetic patients. But turned out to be that is very expensive, because you get a little bit of protein extracted from these animals, but how to give insulin to the patients. So obviously those who were rich, they were getting the treatment. Within 50 years, with better understanding of chemistry of life, they turned out to be that DNA is the genetic material across all organisms, and how DNA information is decoded in the cell to make whatever the information, like for example protein, is exactly the same for bacteria to human, right? And that's a realization, which also an evolutionary biology discovery, helped people to make insulin protein now in bacteria. Because what you do is you take the DNA from human, coding for insulin, put it in bacteria. What bacteria realizes is simply a piece of DNA. It's the same chemical. It's the same chain of nucleotides. It's the same hydrogen bonds between G, C and AT. And it basically synthesizes DNA, RNA and the protein in the same mechanism as happens in the other ones. There may be small differences when it does happen, but when you do at a larger scale, at a laboratory level, now you can make kilogram quantities of insulin in a room like this, and insulin is available free of cost in most government hospitals in India and also in the global south, and except in Trump's America, I guess. And that basically helps, sorry, I know it's being recorded. So now that it happened about 125 to 130 years. It's a slow process. But look at what happened during COVID time. The now world is interconnected. In real time, we understand each other, understand whatever discovery is happening, and that basically helped to address the COVID problem. Given that one of the major pandemics post-civilization, post-modern living, extreme density of populations in big cities, extreme mobility of people from across the world. The virus was spreading like a wildfire, not just within an region, across the world. Even then, we could contain, although we lost a few million people of our other humanity, but we could manage to control it within 1.5 years with developing vaccine, vaccinating billions of people. All happened because we were exchanging the knowledge in real time and converting the knowledge into a product, right? And that's what science is progressing. That's how the science is progressing. Now, coming to Indian context, the reason I want to start this story, which is how to give you one, contextual thing. Science is global. Doesn't matter where something is discovered about the real world. If it is validated, turned out to be correct, it is global knowledge. Whether it is about Earth, whether it is about galaxies, whether about atoms, about life, chemistry of life. But the problems are always local, right? Because in a very complex system that we all live in, the emergent properties can be different in different parts. Look at the climate change. It's global warming happening. Carbon emission is maybe happening more from America or less from other places, but still overall everybody is getting impacted. But the impact is different in different parts of the world. Somewhere is a heavy rain, some may be low rain, some may be cloud burst. In some other place there is a disease progression, some other way crop pests are increasing. Each place is facing different types of problem, right? Agriculture can be affect differently, health can be maybe affected differently. So you had to find solution locally. So irrespective of who produces knowledge, when you want to find solution for agriculture, health, environment, the solution has to come locally. That means innovation has to happen locally. So no country can say that I'll simply buy technology from US or from China and then live happily. It's not going to happen, right? So that's why India also invested in science and technology right from 1947, thinking that we have to invent, we have to discover, we have to invent, we have to develop, we have to innovate locally for Indian problems, right? So one step before I talk about what happened in 1947, we didn't start in 1947 with zero. For example, CSIR were already there by 1947. We already had a community of scientists, fantastic scientists, but smaller in number. If you look at if more and more Nobel Prizes are going to US, right, you think that there are fantastic scientists in US. The fantastic scientists is a fantastic scientific community. The community is very large. naturally the superstars from that community emerging also in big number. In India, we had a very large, small community. How many people were educated even? 12% of the people were educated by 1947. So we are talking about, let's say, Indian history of, let's say, 1875 onwards, when Indian Association of Cultivation of Science was established in Kolkata, the first major scientific institution within India established by Indians who were able to work, Indians to do modern science. To 1947, a very small number, maybe a few hundred people knew Newtonian physics or Einstein's theory of relativity and kind of thing, out of which the number of people who emerged proportionately equally same number anywhere in the world. That means intelligence or talent or innovation can happen anywhere in the world. That's a proof. Look at the number of these people. There are world famous people, J.C. Bose, Raman, S.N. Bose and P.C. Ray and others, right? These are the people who actually made India's science and technology competent. That means when we had in 1947 independence, when people, the founders of that time thought we should invest in science and technology, that confidence came not because they saw science and technology, how it has impacted in Europe and US. It is because our own country, we had such stalwarts, right? Indian Institute of Science was already well known for making fantastic discoveries Ramakrishna is from there. Indian Institute of Science was established in 1909. And many of the scientists at that time, they were basically shoulder to shoulder with Nobel laureates. Not necessarily these people are Nobel laureates, but they're already working at that level, right? So the quality of science was the same with the top level. There was, because the whole community was so small, it was not so visible across the globe. So 1947, when we became independent, as you all know, just few days ago we celebrated 156th year birth anniversary of Mahatma Gandhi. The country won freedom with dignity, self-respect and high levels of morality and ethics because of the kind of freedom struggle we went through using Satyagraha mode of Gandhiji. And that basically helped India to become a democratic country from day one, where there is a universal franchise. No other country even at that time, even in the most developed countries of Europe or US, didn't have universal franchise. For example, black Americans didn't have voting rights, women didn't have voting rights, even in Switzerland until 70s. But India is the first country, such a large country, even when there are so many illiterate people, only 12% was literacy, we gave universal franchise. Same time, whatever we do in science and technology, it should be affordable, accessible to the whole humanity within the country was the first motto. It was not that you make certain products like big mass destruction weapons or you make product which is for elite people, right? It was not the purpose. So the founders thought we need to invest in science and technology to help the masses. That was also the vision of Gandhiji. If you want to pursue science, but make sure that the last person in the food cycle, in the hierarchy of the society is benefited most, right? That's what he used to say. So first thing we had to do, because only 12% literacy, of which very few people knew science and technology, although they were stalwarts. So we had to increase the capability. You had to build dams, you had to build roads, you had to build buildings to build the science and technology institutions. You also had to educate people, train them, right? So the first thing was to training. So the first 25 years, or so about a couple of decades, the reason I put these pictures were, Gandhiji of course was the guiding light, and Nehru was the founder prime minister, the first prime minister. He initiated many of the things that we are enjoying today. And Kalam gave the fantastic support, Maulana Abdul Kalam Azad, in setting up education institutions, right? So first thing was to invest in science and technology was the vision. Second is to invest. First you have to increase the capability to do science and technology. So we established IITs and more research institutions. So many CSIR institutions were set up in the 1950s and 60s. This was established in 1954, I am told, within 7 years of independence, right? And the 50s and 60s, the capacity building, the phase of capacity building, right? You cannot make innovation or product development with only 3 or 4 like Raman and Ramanujan, Ramanujan was not there, Raman or Homi Bhabha and Vikram Sarabhai, some 3-4 mega scientists. You also need large number of science and technology competent people. That's exactly what we did. The next 20 years, we used the capacity that was built in becoming self-sufficient in food and nutrition, particularly green revolution and white revolution. The next 20 years was technological development. That's when the IT revolution happened and so many other manufacturing industries started within India, right? And exports started happening. All of these things happened in the next 20s, and that's when India also liberalized the economy, and because we were confident that we can now liberalize the economy. And next 20 years, what most of you, maybe students here born after 2000, I guess, what you see is all happened based on the foundation that was set up in 1947. We started reaping the benefits of it with modern infrastructure. It could be airport, it could be highways or expressways, and massive fast trains or whatever, right? And also massive expansion of economy happened in the last 20 years. The next 20s onwards, we are now started thinking ahead, what should be our vision for the next 25 years, how India should be, should progress, in which direction, where are the, shortfalls, because we still have huge inequity, right? So we are one of the largest GDP countries, and now it is the 5th largest, very soon we will be 4th largest, perhaps in another 5 years we will be the 3rd largest economy. But that's not going to solve the problem, because look at this, 1.5 billion people as of now. Perhaps the way population growth is happening, fortunately we may not cross beyond 1.5. We actually may have a slow rate of, or even a negative rate of population growth. But per capita GDP is very, very low. That's so work in progress. We still have to generate equity in food, equity in nutrition, equity in health, equity in access to water and shelter, right? So that until we achieve that, we cannot call ourselves as a developed country or a progressive country. And to do that, again, science and technology helps. This is where modern science and technology, this is the the roadmap for the students of today. People like me are already close to retirement. So unfortunately, we may have solved some problem. We means our generation people, not me. We may have solved some problems. We have created more problems, like the plastic problem that Ramakrishnan was talking about. But now, unfortunately, it is the burden of the next generation to solve some of those problems. But you're also fortunate that there are multiple better tools available for you in both in biology, in physics and chemistry, and in computer science to solve those problems. Artificial intelligence, quantum technologies, and gene editing technologies, and so forth, the metabolic engineering. Without exploiting the environment, perhaps you should be able to solve many of the problems of the basic needs of food, health, and nutrition using modern technology. So the future is really bright, but at the same time, today we see lots of problems, it's somewhat bleak. Now, I want to talk about, I'll skip some of the slides simply in the interest of the time. Some of the stories, the main title of the talk. This background context I had to set up, although I could always given some 5 interesting stories, but the stories are not going to be very impactful unless you give the background. The reason the background is important is you want to understand in our history from where we have come from. For example, India is 1.5 billion, fantastic biodiversity of humans, fantastic natural biodiversity, fantastic diversity of languages, culture, practices, and kind of a thing, lifestyle practices. That you need to understand the origin of all of these things, from where we have created this kind of a country with so much of interesting diversity, which is the pride of India. That's the one part of the human history. Similarly, when you talk about how we have solved some of the basic problems of life using science and technology, you also have to understand from where we started. 1947, with absolutely no science and technology base, no major infrastructure in the country except railway that was built by British. There are only 2 or 3 major scientific institutions like Indian Institute of Science and a couple of universities which are doing very well, and perhaps 1 or 2 CSIR institutions which were established pre-independent time. But everything had to be done from the scratch. You had to be built from the scratch and starting from the capacity building. That's why the story was very important, and it will become even more impactful, right? So when you build discovery from a place where you didn't have anything, it is like a rag to riches story, and then you basically narrate that story, the impact is even more, right? So this is the book. You can download this book. It is published 6 years ago. It has 11 stories. There are many such stories and making, but we had to sit and write. With all these stories, people went around and collected evidence, data, made oral history of the people who contributed to these stories. So they're all evidence based, except that the narration is like a storytelling narration, just because it's written for the public, general public, not for scientists. So there is less science in the stories, but the more the stories are in those stories, right? Okay. I'll start with one simple one, plant tissue culture. The fundamental nature of plants is, particularly the large land plants, they can de-differentiate. So all of us, including a really sexually reproducing organism, whether a human or an insect or a plant, they start with single cell. The single cell divides multiple times, and then finally they differentiate into different types of cells, different types of tissues and organs, and finally a whole organism comes, including me, for example, made up of 50 trillion cells. Within 9 months, from a single cell, I came out from mother's body with 50 trillion cells. And there are muscles, there are neurons, and all those things, right? And if you see under microscope, they look very different. And those cells, they stop dividing and differentiate and do their function. But in case you need to replace them because of wear and tear or because of wound, there are division competent cells which are kept aside called stem cells. They are the ones who divide and differentiate and do the job of regeneration. In plants, interestingly, you can take any cell from any differentiated one, a leaf or a stem or root, you can de-differentiate. That means they can start dividing again, make a callus. That callus can actually give rise to the entire new plant. So Professor Maheshwari and his student, they are the ones who actually made some of the seminal discoveries, fundamental discoveries on why plants can, how plants can de-differentiate, whereas animals can't do it, right? That finally led to whole plant tissue culture revolution, because you could start doing this for agriculture purposes, which I don't have to explain what is plant tissue culture. In fact, the major international meeting that happened in 1964 in Delhi University, where who is who in plant tissue culture or plant regeneration came to India to attend this meeting. By the time Maheshwari was very famous, he was a fellow of Royal Society and so forth. When the plant tissue culture as a industrial application actually was born in that meeting, and rest is history. It's a several $1 trillion industry now. Now, milk revolution, all of you know, it's actually a cooperative movement. It's a social movement for start with. So you collect the milk from whoever is producing, irrespective of whether you need it or not, and then together you'll have a large amount of milk. You pasteurize, you convert into very different products like milk powder or cheese or other things, so that farmers throughout the season, throughout the year and all seasons, they get their value for their milk. So they are also encouraged and incentivized to produce more milk by taking care of the cattle and having more cattle and growing more grass for the cattle and so forth. But the second part of nutrition revolution was not only cooperative, there is science and technology comes. The first one was, most infants in India, because of mothers were malnutritioned, right, because of variety of reasons, particularly because of lack of food and nutrition, and the children were stunted or low physical and cognitive abilities, they were growing, right. So the only people who could get good nutrition were well-fed, parents, or who could afford baby milk powder for the infant. The baby milk powder was imported in those days from the same Nestle company was making baby milk powder for the whole world, and we used to import from Switzerland. But the only rich people could afford. Most, even middle class people, couldn't afford baby milk powder. So Kurian, who was in Anand, he thought that we should make baby milk powder, and he found out that first he imported baby milk powder machine from Switzerland. He couldn't make it because the Indian milk is high fat content. That machine that was used, it couldn't generate the fine powder which get dissolved immediately after putting in water. That baby milk powder is for absorption for infant. It has to be extremely well fine powder so that there is no problem of digestion. Right? You are talking about infants like 1 day, 2 day, 1 week, 2 week, or 1 month old infants. So what he did was he approached some physicists in the Institute of Science and some engineers in CFTRI in Mysore. They came together, they sort of looked at the problem, the viscosity, very different aspect of it, and chemical engineering aspect of it, and finally they built a baby milk powder in CFTRI and shifted to Amul, and Amul started making baby milk powder. So because it was done in India, the cost also came down. At least middle class people could afford baby milk powder, which happened in as late as early 80s or late 70s. Look at this. We actually for 30 years we lived in utter poverty with lack of good nutrition for kids. But things started changing in 70s and 80s because of green revolution and white revolution. Another interesting component of science and technology helping nutrition revolution is, irrespective of what happened, then the next part is the children, let's say age 1 year and above. They also need good nutrition. Milk is again the best source of nutrition, right? In Indian context, because the availability of other nutritious food is not so affordable to most of the people, right? So to get the milk at doorstep was a problem. One is milk was always sold in bottles, or the refrigeration was not there. Refrigerated system of transport was not there. Most even shops didn't have a refrigerator in those days. I know I grew up in a time when 1980s itself, in place like Dharwad where I grew up, none of the shops except some big shops had refrigeration, right? In refrigerator in the shops. So he spoke to Varadarajan. Varadarajan was the director of IPCL in Baroda at that time. IPCL is the one which later sold to a private company. It was a public sector undertaking, like many fantastic public sector undertaking of that time, which helped building India. And Varadarajan said, okay, it's a chemical engineer problem. Let me talk to my polymer chemist. So he spoke to young scientists at that time, who happened to be your RAC chair now, and became a director of NCL, Professor Shivram. The Shivram and Varadarajan actually came out with how to make plastic sachets. Even today we are all buying Amul or any milk in plastic sachet, right? That plastic sachet was actually developed through an R&D of IPCL in Baroda, where you had to make a food grade plastic and it should withstand high temperature when pasteurized milk is filled, and then you put a little bit of nitrogen gas and seal it, and then it actually stay for at least 24 hours without refrigeration and a couple of days or 3-4 days with refrigeration. That helped to sell milk at low cost at the doorstep of people, right? Although I shouldn't, as a scientist, I should not give causation to everything without evidence. Look at the correlation. Since this happened, the two things happened: milk, baby milk powder and milk at doorstep. 10 years later, India started winning cricket matches, and AIT-JEE became a big hit because everybody wanted to put more effort and focus on passing that exam. That means your both physical activity and mental activity increase like anything, although it has its own negative impact, both in sports as well as for academics because of IIT-JEE examination. Anything we overdo, we always spoil it. That's exactly what you are saying. Overusing the plastic is the problem, not the plastic themselves, right? Okay, so another story, Penpal. Penpal is the first startup in India where startup was not even termed anywhere in the world as startup, right? It was basically a small garage shop. The reason the way it started is in Sri Chitra Tirunal, one of the DST institutions now, a famous Dr. Valiyathan, who was one of the fantastic discoverer, inventor of modern medicine, and he also combined traditional medicine and modern medicine, and a scholar, and he died recently. Valiyathan was basically trying to see whether we can develop our own blood bags. Until late 80s, India had to import blood bags. Blood banks as a concept was there only in big cities like Bombay and Delhi and Kolkata and Bangalore and a couple of places. I don't think even Ahmedabad had blood banks. So people, if I had to get blood donation, the donor has to go, they test the blood group and ask them to, lie down on the bed, and the bed there will be the receiver, and the blood goes through a bottle from the donor to the receiver. That was the state. And you couldn't get good quality blood all the time. If you don't get the right group blood at that time, because there was no storage facility, then people had to die, right? If there is an accident, there is no way to give blood transfusion right at the site of accident, people would die. So he thought we should have our own blood bags, which will be affordable, so that the whole country should have blood bags, so that blood banks can be established in smaller towns too. It took 10 years for them to establish. A lot of science went in, a lot of chemistry, a lot of chemical engineering set up. Finally, they made blood bags because it has to get aseptically filled. Aseptically, it has to go to the receiver. The donor to the blood bag to the receiver, everything has to be done in extremely aseptic conditions. So whole thing, and what is the quality of it? It should not be any aeration also at the same time. Whatever the gas that you fill in, keep the blood in a living condition. Other than that, should not be any contamination from outside. Even the gas should not have should not exchange through the membrane. So that took that, and now India exports blood bag to 80 different countries. It's the largest producer of blood bags in the world. 80 different countries are dependent on Indian blood bags. See how many lives have been saved, not just in India, across the world, at least global south. Millions and millions of people have lives is saved because of 3 or 4 people who worked to developing blood bags in India. This I'll skip. You can read in the book. There are so many such stories. I'll tell you one other story. I'll tell you 2 more stories. This one and the one next is closer to your home. IT revolution. All of us think now in the last 30 years that India's wealth, the modern infrastructure, modern living, everything because of digital revolution and IT revolution. Not only it provided all the gadgets that we are using for convenience, at the same time, it also produced so much wealth in the country because of our ability to provide IT services to the whole world, right? But how it all started? Extremely interesting story. It's you need intelligent, visionary people to be at the top of the place to achieve and have such foresight. So the first computer came to India in 1955. It was a donated computer, like many things were being donated to India at that time, because India was one of the poorest countries. We used to get donations. Food was a donation, and also many other things. One of them was also a computer. A used computer was given to India by IBM, saying that I want to give this computer for your purpose. Can you use this? And because the community was very small of science and technology, and who takes a decision was not so many intelligent people were around to take decisions. The most well-read, most intelligent, most well-connected person at that time amongst the few scientists was also Prime Minister of that time, Nehru. So they actually directly contacted Nehru whom to give this computer. So Nehru asked a couple of people. He asked Homi Bhabha. He also asked ISI Calcutta founder Mahalanobis, a famous statistician from India. And both of them said, give it to us, we'll put into best use. One said, I want to do a lot of number crunching for statistics so that we can actually do social welfare, we can do better fire planning, we can do economic planning with social justice and kind of thing. Whereas Homi Bhabha was thinking that, we can actually do energy self-sufficiency, we need this kind of a computer to do number crunching for atomic energy research. But finally, Nehru thought, both of them are good reasons, so he requested IBM to give 2 computers as donation, not just 1. So 2 computers came, one went to ISI Calcutta, one went to TFR in Bombay, at that time Bombay, now Mumbai, Colaba. So what Homi Bhabha did, he's a researcher, he's also a basic science researcher, he's not only a technocrat, right? So he asked Narasimhan, who was a young faculty at that time, just returned from Caltech, said, why don't you do research on computer? Rather than simply using computer for what we think can be used for, why don't you do research on computers so that we can actually diversify, not only make computers within India, also diversify, right? Although now we import most of our computers, including our mobile phone and laptops and desktop. In fact, they actually built computers in TFR, and more importantly, they started diversifying the applications of computers for a variety of different things, not just for research and also for very different operational purposes, right? That led to establishment of ECIL, Electronic Corporation of India Limited, which is one of the largest PSUs even today in Hyderabad. CDAC, which now CDAC value has come down because of so many private players, but CDAC, one of the largest computer software support system in the country. Department of Electronics was established on suggestion of TFR director at that time, M.G.K. Menon. They said, why did you come and establish? So he had to leave TFR and go to Delhi and to establish Department of Electronics. National Institute of NIC, all our, your website to your email system to every government, IT system is maintained by one organization called National Informatics Center, and that was established by a professor from TFR, Sheshgiri. They all became, not only they helped to build computers, use computer for research in their own organization, they actually contributed to the whole country in very different ways. Not only that, they opened up TFR Computer Center for anybody to use. People from Indian Institute of Science to very different universities used to come to use computer for research. In addition, if you look at some of the people who have used computers here. Okay, yeah, here. Look at Air India, Best is basically Tata Electric supply company. Hindustan Lever, Godrej, Larsen & Toubro, Sandoz, Oil India. Just look at any of those large firms, anywhere with have 500 employees and above. they actually started using computers for their regular day-to-day operations with help of computers in TIFR. That increased the computer utility, increased the computer literacy, and the need for computers in the day-to-day operations. That actually built a whole kind of an ambience that where government started thinking that yes, we should computerize. Then in 1887, when Rajiv Gandhi was the Prime Minister, when the computer industry started growing, because that's when the decision was taken that computers should be introduced at all levels of our administration and very different aspect of our life in general in the country. And that basically led to IT revolution. The one last point of dot in the IT revolution is some of the students of TIFR and Indian Institute of Science, they became faculty in IIT Kanpur, and they were computer literate, they were using the computers. The first thing they did, because an undergraduate teaching program, is to start a BTech computer science program in IIT Kanpur in 1964. It is the second in the world to start an undergraduate program in computers. It is not US is the first one, Purdue, the second is India, not Japan, not UK, not France or Germany, not even another university in US, it is the India. See, that's what I'm thinking of. What you have to understand is humanity in particular is the Indian scientific community may be small, it may have less resources, we didn't have all kinds of gadgets to play around as a scientist or instruments, but the thinking, the foresight was not any less than anywhere else in the world, right? And that's what made these people to contribute in such a big way. The impact of IT revolution, just think about it, unimaginable impact, right? I don't think ever of any of these people could imagine. That's what I'm saying. Always scientists are ahead of time. Invariably, each one of you as a scientist are always ahead of time compared to public, because you always think of what can be done with this knowledge in the future. You don't think that this can be used for today, right? And you yourself will not know that what is the impact of it. You look at from hindsight, oh, fantastic impact we have made. Today morning we were talking about the impact of seaweed industry that you people have contributed. It apparently is more than 300 crore worth of business to the industry, which has taken one particular IP from you, and also has helped several thousand farmers, right? That's the impact, right? That's what called unimaginable impact. It's not necessarily that you have millions of people that have benefited. Even if few thousand people get benefited, you have improved the quality of their life, you have saved their lives, generated livelihood for them. That's also an impact. Okay, last one is this. There are many more studies, but I'll just, in the interest of time. Diamond. I'm told today when I was traveling to Bhavnagar, the first time I heard it, I always thought that diamond means Surat. So I'm told Bhavnagar is also a small diamond capital, right? I don't know how big it is, but looks like it is a diamond capital in its own way. So traditionally, Indian diamond jewelers are diamond jewelers, not diamond merchants, right? They used to get cut and polished diamond from Antwerp in Belgium and use it for jewelry, embed in jewelry, and then export or for internal use within the country, right? That's what basically diamond jewelers are all about, right? And in 1980s, right? No, 70s actually, 1970s. Vikram Sarabhai, I'm sure all of you know Vikram Sarabhai, right? He is a fantastic scientist, visionary. He established Space Research Institution, even in 1950s where we didn't have enough food for everyone, but he still thought, both Bhabha and when people like Sarabhai were insisting for high quality and high end research in a country with such poverty, was also saying that this is also one of the methods of alleviating the poverty. You are not doing simply for the sake of luxury of doing science. This science is going to help the next generation, if not this generation, because we have to improve the quality of life with the help of science and technology. So Sarabhai established science outreach center or science education center we call. Now it's called Vikram Sarabhai Science Center. Basically to improve the better understanding of science among the public, like your open day. I saw so many people from the public schools and colleges come and try to understand what people are doing. The purpose is to make public aware of science, and its importance in our daily life. So two students, diploma engineering student, they heard the talk by Professor U.R. Rao. He was a very famous space researcher, and he apparently mentioned about lasers, and he said lasers are so powerful Lasers are not known even in most part of the world. It's not forget about, only scientists knew what lasers are and they were using for scientific purposes, not so much for day-to-day use, right? So he said, lasers are so powerful you can cut and polish diamond. Because diamond is considered as the most, the toughest material, right? That caught on to their, head, these kids, and they actually built their own lasers with the help of, some gadgets, and they actually could convince themselves, right, directly as a proof that they can actually cut and polish the diamond. They took those lasers, guns to Surat to convince some diamond merchants, wanting to buy this, you can actually cut and polish. Those days, cutting and polish, but because already polished diamond you hardly had to do fine cutting and polishing just to so that you can properly embed in the jewelry. You had to sort of do something. They were all afraid that if you use laser, which is an unknown thing, what if I cut in a problem way, because diamond is so precious, if I miscut something, I would lose the whole diamond, right? So that's why they were also reluctant to use. It took about 1 year for them to convince at least one diamond merchant to use the laser in their business. Slowly it picked up because everybody realized that small laser gun can be used with the same precision as like a pen in your hand, right? So that led to, massive reduction in the cost of cutting and polishing because they were using lasers with same precision, and because then Surat became an attractive place to cut and polish diamond. So the raw diamond used to go to Antwerp. From Antwerp, we used to come to Surat for cutting and polishing. I'm sure to Bhavnagar also. Sorry, I keep mentioning only Surat because that's the only story I know, right? And then basically now Surat became not just jewelry shop, it's also cutting and polishing of diamond. Then Nelson Mandela came, apartheid gone. The reason Antwerp became diamond capital, Antwerp in Belgium and also Amsterdam in Netherlands, all because of the Dutch colonization of South Africa, and most of the diamond mines were with them. When the government changed, there was also democracy and a little bit more liberal attitude, that raw diamonds started coming to Surat directly. And then cutting, polishing, jewelry, merchandise, everything is happening from India now. Antwerp is almost removed from the global map of diamond industry, right? So that's the power of just one good science talk a scientist could give and enlighten people. And also look at how much value has happened to the city of Surat and to general country's economy because of such innovation and application. And this is 2014. I even stopped looking at it because I know it is not even worth, because India is the largest diamond industry now. Cutting and polishing itself, you look at the share of cutting and polishing is more than 70% in 2014, 10 years ago, 11 years ago, right? It all happened within 30 years, from almost all the things were happening in Antwerp to Surat becoming or India becoming the largest diamond market in all aspects of diamond, starting from raw diamond cutting and polishing to embedding jewelry, the diamond merchandise, everything is from India. Many such interesting stories. Shamunat Dey, Dilip Mahalanobis, their work has saved millions of lives with India as well as in global South, including South America and so forth. The story is being told already, but still there are lots to discover about their work, how they contributed. Professor Lamu Swami is the one who actually discovered the importance of iodine in our diet, and through iodine comes through the salt, and now iodized salt is made mandatory in India and also in many countries wherever there is a problem of iodine deficiency. And also the way we contributed to COVID. India has immensely Indian scientists, scientific technology community, right? For example, most testing centers were actually run by scientists because there were not enough RT-PCR, not many people knew how to do RT-PCR test. But all biologists like us who do molecular biology in the lab, RT-PCR we do day and night. Whether we use for plant RNA or for bacterial RNA or human RNA, it's not going to make much difference. It's simply an RT-PCR. It's a chemical reaction in a box, right? So we could actually increase to 12,000 centers within 1 year. We made kits. We came, India is the only place where kits were available at any time. 1 million kits per day we are producing within India, generating reagents, including DNTPs. DNTPs were not made in India until the 2020s. Only during COVID we started making DNTPs in India. Then although we had some fantastic organic chemistry, knew all about nucleic acid chemistry, right? The cost of test is the lowest in India compared to anywhere in the world during COVID time. We were doing it for 200 to 250 rupees when the Delta wave was hit in the country, right? Although we started with high. Then 2 vaccines were produced, and then, every Indian, adult Indian was vaccinated within 1 year. That's how we came out of the pandemic. Anyway, there's so much to do. This is all the things that we need to do, particularly for both those who are biologists. These are the issues we need to address for the coming years, but there are tools available. The community is much large. Knowledge is democratized, is accessible to everybody. The problem that you have may be a larger problem, but the success of the first 75 years of India should empower you and give you sufficient confidence that you should be able to solve the problem for which better tools are available, better infrastructure is available. For example, when the first rocket was launched, people had to carry rocket on a bicycle because there were no good roads to take them in a vehicle. The only way carefully you can take is, instead of putting their on the shoulders and carry manually, they were using the bicycle. That's all, the only difference. But the thought process was ahead of looking at the sky, right? So you people have better infrastructure, better tools available now in science and technology to address some of these problems. I'll stop here. Thank you.
प्रोफेसर शशिधर, स्वतंत्रता के पहले और बाद में भारतीय विज्ञान की यात्रा और उसका समय के साथ संवर्धन और अनेक रोचक वैज्ञानिक कहानियाँ और कोविड-19 में भारतीय विज्ञान के योगदान आदि मुख्य विषयों पर अपने विचार साझा करने के लिए आपका हार्दिक धन्यवाद। अब मैं सभी माननीयों से पुनः सामने की ओर बैठने का निवेदन करती हूँ। उससे पहले मैं हमारे निदेशक महोदय से अनुरोध करती हूँ कि वे हमारे वक्ता प्रोफेसर शशिधर को स्मृति चिन्ह प्रदान करें। दूंगी कि वे स्थापना दिवस संबोधन के लिए मंच पर आएं। सर, आपका स्वागत है।
Yeah, I think it's settled. Okay, fine. Good evening, Professor Shashidhara, Professor Ramakrishnan, Dr. Ganguly, Mr. Biranchi, and my colleagues, both present and past, and those who are attending through online. I know that there are several people, maybe some of my fellow colleague directors who may be attending this online, my fellow colleagues from CSIR who may be present in the online, and all the well-wishers of CSIR family and CSIR CSMCRA family. First of all, I mean, a very, very, I mean, what do you call, proud moment that we celebrate 84th CSIR Foundation Day on this occasion. And I mean, extend my warm wishes on these special occasions. I'm sure that most of you, if not all, I mean, most of you must have witnessed, as Dr. Ganguly was pointing out, about the CSIR Foundation Day celebrations that had happened in New Delhi, which our Honorable Minister, who is the Vice President of CSIR, has, I mean, given a kind of talk. And in fact, I mean, I just wanted to take a cue from what Professor Shashidhara was mentioning. He used 2 words, okay, but he used 3 words. Our minister used 3 words, and you have used 2 words, but all of them are what you call sounding the same. So affordability, accessibility was the 2 words that used. He also said about the same 2 words. And in addition to the this thing, he used one more word which is called as awareness. Okay, so this is something which is a kind of an, he used, the take-home message for all of us who were present in that Beam auditorium was, whatever the technology that we are developing, it should be basically made aware to the people, and it should be affordable to the people, and it should be accessible to the people. And that's what is all about. And CSIR as an organization, as Professor Shashidhara also mentioned, several stories where, CSIR Labs was coming left, right, and center. If you guys have very critically noticed, essentially, the organization was positioned as a science-driven technology leading into a kind of a humankind welfare was the what you call fulcrum with which the organization was built. And in the last 84 years, we have been basically pushing hard on that what you call forte. And whatever we are doing it at the institute, at this institute or across the CSIR, this is with the same kind of enthusiasm and impetus with which we have been what you call doing on it. And of course, you know that I give on 2 occasions, and of course, I'm sure that you also must have listened to the word of Dr. Panchanathan, who was the former director of National Science Foundation, the United States of America, who gave a principle called as TIGHT. Okay, TIGHT. I just only use one word, T. The rest of the things, especially for the students, please listen to that lecture. It is worth listening it. And T means for talent. Okay, so that is one of the things. IGHT, what does it mean? I have it here, and I know I don't want to tell it, or else you will not see the lecture. I wanted you to basically go and then see that lecture. Essentially tells that, okay, there are certain traits necessary for scientific fraternity. As he rightly said, we are a very small fraction of the whole of the population. Okay, as we speak today, the full-time equivalent researchers of this country is only 300,000. That is, I'm putting it in a maximum number. And what is our population? It is inching towards 1.5 billion. So we are a very, very ultra small fraction. And our responsibility and accountability is very, very large. Because whatever the discoveries that has been, he mentioned, which has happened between 60s to, let's say, for example, 1990s or early 2000, he discussed. But somebody who is a kind of a predecessor of Shashidhara should come and then tell in this auditorium in 2060 and 2070, what has happened in 2000 to 2050, which basically shaped Indian science and technology. Okay, at that particular point of time, whatever we are doing today, not as an institute, but as an organization as a whole, should be reflecting on it. And that's how we should be basically positioning ourselves. These foundation days are essentially meant for reflecting on those kind of commitments. And unless otherwise, because the world is changing extremely fast. The world is changing extremely fast. What is the challenge which those guys were not having it? The one that we are having it today. The reason is information is so much abundantly available. And information is unfortunately unilaterally available, unequivocally available. Under these circumstances, the competition is also very large. And unless otherwise we don't solve the problems of our country, nobody else will be coming and then solving the problems. Don't expect, people from the other countries to come and then solve your problem. No. We can take the help of the people because science is global. But that doesn't mean that, we should not be working for the problems of our country. Whether it is on the resources or whether it is on the diseases which is prevalent in this part of the world, or whether it is on the energy security. These are all critical problems for our for our nation, because we say that we wanted to grow with a kind of a pace which unfortunately many countries are not growing. More than 100 countries will not grow are currently growing at the pace at which we are growing. And with this kind of a growth, science and technology only can basically accelerate this growth or even sustain this growth. Science and technology is the only option. There is no other option available. The science and technology led into kind of a manufacturing, led into kind of a services. All the these are all basically offshoot of these particular stuff. And I'm sure that as I said, I generally give two occasions. One on CSMCRA Foundation Day in April and one in the September-October time during our CSIR Foundation Day. So, and I'm happy that on several of the fronts, whether it is on technologies or whether it is on projects or whether it is on research publications or whether it is on human resource creations, we've been doing reasonably well. Of course, area that I told in our council meeting also, and I'm reiterating here. Okay, I think invention disclosures are something which is we have to really buck up, because at the end of the day, the innovation potential of the organization, especially those who are in the translational domain, the innovation potential of the organization determines the global positioning of the organization in the technology space. So we are not fighting only with fewer groups in the institute or within the organization. Our fight is with the whole world. Okay. And now technology is omnipresent. Any technology that is going to be competitive and solving the needs of the society, it is going to come and then replace it. So we need to be a little more pushy on in terms of our inventions. That's one of the messages that I just wanted to give it at this point of Foundation Day address. And I'm very, very happy that several of our new discoveries that had happened in the last 6 months, I'm very, very happy that, which were covered in very prestigious journals, very prestigious journals on several topics, whether it is on metal mining or whether it is on membranes or whether it is on energy security or whether it is on salt, which are extremely core domains for this institute. We have been, we have been demonstrating to the world about the scientific caliber with which we have been pushing. And I sincerely, congratulate all the people who are knowledge creators and value creators. These are all, ultimately creating a kind of a knowledge and value proposition for our scientific fraternity and also as a nation on the whole. And I must congratulate all those people who have been involved. Of course, as I said, in the previous occasion, the institution building is a collective effort. Individual brilliance joining in hands in tandem are only going to basically make our institute to a globally positioned one. Okay, and I'm sure that as Dr. Ganguly was pointing it out, we have CSIR on the whole has made a kind of a 10 commitments, and I urge all of you to watch that video if you have not watched that 4-minute video, which is everyone in the CSIR fraternity should watch. 10 commitments that we have given for Viksit Bharat, and one of the commitments that we have given is on the of the 10 commitments of the whole of CSIR, one of the commitments as given by this institute on seaweeds, and we must accelerate in terms of more number of locations for amenable cultivation of seaweeds and more amount of products coming out from seaweeds, and ultimately many of our seaweeds, especially the edible seaweeds, should be taken into the plates of our Indian cutleries. That's something which is a kind of a proud moment. This is going to be a kind of a revolution. This is, if we are bringing these kind of he mentioned, I'm not sure how many of you have noticed his last slide. One of the things that he talked about is about the alternative protein diet. One of the challenges that he mentioned, six or seven challenges I've written down as fast as possible, and one of them is that. And this is an area that which is very high propensity to deliver it, and we must make use of this opportunity. And this is one way by which we can contribute to the health security of the nation on the whole. And same is the case with the saline agriculture. Same is the case with water security of the nation. All these are all, these R&Ds are surely having a kind of an impact. Today I was having a meeting with DG just before the foundation day. And I've been telling in the past also. At this point of time, 17% of our Indian population, what is our Indian population is 17% of the Indian population lives in the coastal habitats, and our coastal land is completely getting inundated with salinity, and which is absolutely not drinkable water at all. And how are you going to solve the problem? And the desalination is one of the options, one of the very promising options. And that is the reason, Government of India is pitching very hard on it. And there are many excellent reports which suggest that in the next 20 years, India would be building several desalination plants in this country. And we as a CSIR has been proposing about decentralized desalination plant systems in the country. When I was talking about this, our DG went one step ahead. She said, it's decentralized desalination may happen not necessarily in places of coastal places. It may happen even in a kind of a large communities, in a kind of a system. The housing systems also, the way that every housing system has a kind of a gas supply, and desalination systems and the solid waste management systems will become a kind of an integral part of the housing community in the future. And these are all going to be, these are the technical problems which needs to be addressed only through science and technology, where our institute plays a very prominent role. And we know that, we have also given technology transfer commitments. 3 technology transfer commitments have been given, one on seaweed, one on salt and marine chemicals, and one on water. All the 3 are very critical areas. These are not, these technology transfer commitments don't consider it as a kind of an independent responsibility. No, these responsibilities are having a kind of a huge amount of an impact. Like for example, if one were to make a kind of a pure brine, as a kind of solutions, every day we would be basically saving millions and billions of liters of water which is currently used in the caustic and soda ash industries. That's the kind of an impact we are bringing in. These technologies have that kind of an impact, whether it is for the water security or whether it is on the nutritional security using seaweeds. These are some of the areas that we have made a kind of a commitment. And also I'm very happy that we in this last 6 months we have also been, because this institute is has been very delicately balanced, where the knowledge is translated into a technology which is both benefiting industry as well as the society. There are few, societal interventions that we have done in the last 6 months, like whether it is on the distribution of seaweed seed material. We have distributed roughly around 70 tons of seaweed materials to hundreds of farmers who are multiplying into thousands of tons and making a kind of an impact in their lives. And elite germiplasm that we have made in several hundred kgs have been basically distributed. And we have also, in one of the schools in Gujarat, 50 kilometers away from this place, we installed a kind of a very beautifully indigenous membrane which can address even the hardness of the water, which was very hard. In fact, more than 2000 ppm TDS hardness water has been treated, which is helping more than 1000 school children in that particular place in a hill, where water is a very critical commodity. And the mobile desalination plant deployment in Jammu and Kashmir, when the floods happened, water everywhere, not a drop to drink. It happens after flood also. Okay, they did not have any, there are certain villages doesn't have any kind of a water availability at all. And the team has, with a kind of a short notice, within 8 hours of notice, they made the entire plant available, and they went to Jammu and Kashmir, the remotest villages of Jammu and Kashmir, where usually people dare to go. I mean, because it's a stone throw distance to our neighboring country. And there, I mean, they provided millions of gallons of, I mean, thousands, tens of thousands of gallons of water to the several thousands of people. I mean, this is the way, I mean, technology is contributing to the society. And I must, place on record over here on this occasion, very, very, hearty congratulations to all the teams who have been involved in this, social clause. And I think they deserve a very strong appreciation. I mean, with a clap also. Okay, I think, I mean, it's not, these are all, I mean, very, very difficult ground level problem, which we have been, doing it. Of course, I mean, we also had, say, I mean, our science and technology, as Professor Shashidhara was mentioning, it's a global science. At this point of time, we have been supporting at least half a dozen countries all over the world in terms of establishing salt works in those countries. And one of the delegations which has come from Philippines, 15 people came to this, including the chancellor of the university had come, and they all said they searched all over the world and then figured out an institute which is in a kind of a remote corner of a country. They said, I mean, this is the only institute which can help us in making the productivity of salt in their country. And the delegation was also accompanied by the director of the Department of Science and Technology. They all said, I mean, please help us. And we wanted to produce our own salt in our country, which is currently, I mean, they are importing it. 93% of the salt is getting imported, and we are going to help them to make the salt on their own, so that, I mean, they'll have the kind of a pride of taking their own salt, even for their domestic consumption. And there are some very, very interesting projects that we are, undertaking, be it on, carbon dioxide sequestration from the flue gas thermal power plants for, Adani, I mean, Mundra plant, or, I mean, on the single stage seawater desalination. These are all some of the projects which are going to have a kind of a humongous amount of impact. And that's how, I mean, we are positioning ourselves in conducting a kind of a workshop and conferences on these domains. And we have also done a kind of an international conference also, where we discussed about all these domains to the international audience. I mean, just after this was given in middle of September, within 15 days, at least 4 or 5 international people are asking, I mean, we wanted to take your help on these domains. And that's the kind of a power with which, I mean, we've been trying to do. Yes, at this point of time, for making all these things to happen, we need to add more manpower. Manpower is, at the end of the day, I mean, there are 3 things which is necessary for doing any science: good quality, talented manpower, decent funds, and of course, nice infrastructure, and with a kind of a good ambience. I think, I mean, the science, I don't consider, I mean, there's no institution is different. And I must, thank the entire administration team and those who are associated with the recruitment. Several new people have been added in the system, and I welcome all. I mean, although I've not personally met many of you guys, okay, and I welcome you all on this occasion. Be a part of this long journey. You guys are going to be there for at least next 2-3 decades. Okay, be a part of that long journey, and then see that how your work, I mean, be it on administration, or be it on technical, or be it on instrumentation, or be it on support systems. I mean, every piece of a corner, every piece of a building is important for our growth. I mean, it's not one section is important, another section is not important, because at the end of the day, I mean, if everything is rightly placed only, I mean, the building will be reasonably strong. And I know, I mean, there are, I mean, several events we have done. I mean, staff welfare measures we have undertaken, okay, and I mean, whether it is on the medical camp, or creating a kind of a travel help desk, or I mean, making our colonies relatively better place to live. All these things are necessary. I mean, because at the end of the day, I mean, we spend 8 to 10 hours of our day in the lab, and then when we go home also, we should have a kind of a peace. And we are trying our best to provide that kind of an environment. And as I said in my previous occasion, it is not the size of the institute matters. The dream of the institute only matters. And let's have a kind of a dream high, because the projects that we are undertaking, they're all, in fact, I mean, DG was asking me, why are you taking so much time? I said, last 3 years, we have done thousands of experiments, and 800 of them are failures. Science doesn't come, and science is not for weak-hearted. I mean, those who are basically backbenchers, please consider this. Science is not for weak-hearted. Science gives you surprises. Science gives you challenges. Science gives you tears. And you have to be resilient in overcoming that. And I take on this occasion, I mean, we are very, very small section of a people who are trying to make a kind of a change in the large section of a population. So we should be different from them. We should be different from them, and that's how we basically place ourselves. And I say, I take on this occasion that every one of us rededicate ourselves on these occasions, that we serve for this organization for its greater heights. And I sincerely, congratulate you on all these on these occasions, and I offer my best wishes to you. Thank you very much.
निदेशक महोदय, आपके इंस्पायरिंग संबोधन के लिए आपका धन्यवाद एवं अभिनंदन। अब हम कार्यक्रम के अंत की ओर बढ़ रहे हैं, तो मैं प्रशासन नियंत्रक श्री विरंची सारंग जी को धन्यवाद ज्ञापन वोट ऑफ थैंक्स के लिए आमंत्रित करती हूँ।
आप सभी को मेरा नमस्कार। आप सभी को एक साथ हैप्पी बिलेटेड बर्थडे। हमारे संस्थान के आदरणीय निदेशक महोदय डॉक्टर कन्नन श्रीनिवासन, माननीय मुख्य अतिथि प्रोफेसर एस शशिधर, निदेशक नेशनल सेंटर फॉर बायोलॉजिकल साइंसेज बेंगलुरु, विशिष्ट अतिथि प्रोफेसर एस रामकृष्णन, डिपार्टमेंट ऑफ इनऑर्गेनिक एंड फिजिकल केमिस्ट्री, इंडियन इंस्टीट्यूट ऑफ साइंस। इस समारोह के समन्वयक हमारे चीफ साइंटिस्ट डॉक्टर विश्वजीत गांगुली, डॉक्टर पारुल साहू और आयोजन समिति के सभी सम्मानित सदस्यगण, यहाँ उपस्थित हमारे सहयोगी, हमारे पूर्व सहयोगी, हमारे छात्र, आप सभी को सादर नमस्कार और हृदय से धन्यवाद इस अवसर पर सम्मिलित होने के लिए। भारतीय परंपरा है अतिथि देवो भव। हमारे अतिथि अपना बहुमूल्य समय में से हमारे वैज्ञानिकों को, हमारे छात्रों को अपना मार्गनिर्देशन देने के लिए समय निकाला। आप लोगों का हृदय से धन्यवाद सर। प्रोफेसर एस रामकृष्णन जी ने जो एक प्लास्टिक एक वरदान और एक विनाश पे जिस संतुलित ढंग से अपना व्याख्यान, बहुत छोटा सा टॉपिक में जिस तरह से इन्होंने संतुलित ढंग से हम लोगों को बताया, वो सचमुच विचारोत्तेजक है, हमारे विचारों को बढ़ाने वाला है। और साइंस में सबसे महत्वपूर्ण चीज़ होती है सीडिंग। इन्होंने बताया सीडिंग सबसे महत्वपूर्ण चीज़ होती है। कौन सा विचार, कौन सा व्याख्यान किस व्यक्ति के दिमाग में कौन सा आइडिया लाए और वो आइडिया यूरेका करके एक नोबेल प्राइज़ हमारे CSIR को ले आए, हमें नहीं पता। मगर आपने सर सचमुच बहुत अच्छा व्याख्यान दिया। और जैसे प्रोफेसर शशिधर ने साइंस के हिस्ट्री को बताया था, उसी तरह से हमारे CSIR की 3 संस्थाएं IIP, NPL और CRRI, इस जो राक्षस नुमा ये जो प्लास्टिक का ये शुरू हुआ है, उसको ख़त्म करने के लिए, उसको आपने बताया छोटे मॉलिक्यूल्स में करके प्लास्टिक टू डीजल, प्लास्टिक टू टाइल्स बनाने की दिशा में, प्लास्टिक से रोड बनाने की दिशा में बहुत तेज़ी से काम कर रही हैं। और जल्दी ही ये जो बून हमारा बेन बन रहा है, शायद हम लोग उसको फिर से बून की तरफ ले आएंगे। डॉक्टर शशिधर ने भारतीय विज्ञान में का जब वर्णन किया, तो जिस समय इन्होंने भारतीय विज्ञान का वर्णन किया, हम लोग अमूल को जानते हैं, इसको जानते हैं, मगर उस समय CFTRI को नहीं जानते हैं। हमेशा से CSIR इतिहास, जिस समय भारत का स्वतंत्रता संग्राम के बाद भारत का जन्म हुआ था, हमारे पास कुछ नहीं था। और CSIR की स्थापना भी शायद इसीलिए की गई थी कि इतिहास में कि हम इतिहास बना सके। हर एक उस छोटी छोटी ज़रूरतों को जिसकी हमारे समाज को ज़रूरत है, वो आप लोगों के माध्यम से यहाँ छोटे पैमाने पे रिसर्च करके बड़े पैमाने पे समाज में वापस दे सके। इसीलिए CSIR की स्थापना हुई थी। सर ने CFTRI का उल्लेख किया। कोविड के समय में हमारी 3 संस्थाएं CCMB, IGIB और IIMT दिन रात मेहनत कर रही थी सर, जब हमारा वो DNA का पैटर्न बदल रहा था हमारा कोविड। और कोवैक्सीन और ये आ रहा था, तो उस समय हमारी 3 संस्थाएं दिन रात का ये कर रही थी। IIP एक केमिकल लैब थी, जो इन्होंने सर ने बताया कि 2 से हम लोग 12,000 सेंटर पे पहुंच गए थे। केमिकल कम बायोलॉजिकल केमिकल लैब ही मुख्यतः है IIP। उसने सर 30 दिनों के अंदर सारे लॉकडाउन के बाद भी एक जो है सो जांच सेंटर, कोविड जांच सेंटर बना दिया था। और हम लोग इसके लिए हैंड सैनिटाइज़र के लिए तो खैर हमारे सारी संस्थाओं ने, पुलिस वालों को, CRPF को, CSIR की अक्रॉस द इंडिया सारी संस्थाओं ने मतलब जो योगदान दिया। ये सब बातें मैं आपको सिर्फ इसलिए बता रहा हूँ कि ये सब जानते हैं, सर भी जानते हैं, आप भी जानते हैं, सब जानते हैं। सिर्फ ये इसलिए बता रहा हूँ कि ये हमारा महत्व है, ये हमारे जन्म से लेके आज तक की प्रक्रिया है। और इसको जैसा कि सर ने बोला था कि अगर कोई 2070 में बताता रहे, बात करता रहे, तो ये बताए कि जब नमक का आंदोलन जब इस गुजरात की धरती से हुआ, उसके बाद जो नमक की क्रांति इस गुजरात की धरती पे आई, वो CSIR ने लाया। ये आपके माध्यम से लोगों को पता चले 2070 में जब हम लोग अपना फाउंडेशन डे बना रहे होंगे या कोई संस्था मना रही होगी, तो ये बात आए। ये प्रेरणा सर ने आपको अपने माध्यम से दी है। सर ने बोला कि मेडिकल कैंप लगाया, छोटी सी चीज़ है, आप लोग रिसर्च करते हैं, बहुत ज़्यादा स्ट्रेस है आप लोगों के ऊपर। इन्होंने बोला कि हज़ारों एक्सपेरिमेंट किए, 800 फेल्यूर है। आइंस्टीन ने भी शायद 1000 किया था, उसके बाद 1001वां में वो सफल हुए थे। 800 फेल्यूर कभी भी आप अपने मेंटल टेंशन में ले लीजिए। सर मैं अगर आप कहें तो सर ने एक प्रोग्राम बनाया है, एक लेक्चरशिप अगले 1 साल में आयोजित कर रहे हैं, जो आपके मानसिक तनाव को, आपके मानसिक प्रोडक्टिविटी में कैसे बदला जाए, अलग अलग विशेषज्ञों को लाके इस संस्थान में आपके लिए लेक्चर दिलवाया जाएगा, ताकि आप अपने टेंशन को अपनी पॉजिटिविटी में बदल सके। जो असफलता होती है उसी में सफलता छिपी हुई होती है। हटा दो, सफलता आ जाएगी आपके पास। 1 स्टोन अवे, अंतिम हथौड़े की अंतिम चोट से पत्थर टूटता है, इसका मतलब पहले चोट का महत्व खत्म नहीं हो जाता है। जब तक पहला चोट नहीं पड़ेगा, अंतिम चोट से वो पत्थर तोड़ने का नहीं आएगा। तो सर आपका बहुत बहुत धन्यवाद, और सर आपका भी हम लोगों को इतने सही तरीके से मार्गदर्शन करने के लिए। इस अवसर पे डॉक्टर गांगुली सर का और उनकी टीम का, जिन्होंने एक एक धागे को, एक धागे में सारे मोती को एक एक ढंग से पिरोया है। कब टिकट करना है, कब होटल बुकिंग करनी है, नाश्ते में क्या आएगा, खाने में क्या आएगा, जो बारात के पीछे का सिस्टम होता है, इस चकाचौंध को सब देख रहे हैं। इस चकाचौंध के पीछे कब शॉल, कब फूल, कहाँ से, ये जो इन्होंने जिस तन्मयता से और जिस कुशलता से इसका प्रबंधन किया है, सर आपकी और आपकी टीम को, जिसमें मैं भी शामिल हूं, हार्दिक धन्यवाद। थैंक यू। हमारे सेवानिवृत्त कर्मचारीगण और जिन्होंने 25 साल की अथक सेवा दी है इस संस्थान को, वो यहाँ आए, हमने उन्हें सम्मानित किया और हम लोग खुद भी सम्मानित हुए उनको सम्मानित करके। आप सब लोगों का बहुत बहुत धन्यवाद। साथ ही वार्षिक रिपोर्ट और प्रौद्योगिकी संग्रह, जिसके लिए डॉक्टर कांति भूषण पांडे जी ने काफ़ी अथक प्रयास किया था, और उनकी टीम ने, सब लोगों ने, ज्ञानांतरण की गतिविधियां, वार्षिक रिपोर्ट, उसको छपवाने से लेकर एडिटिंग तक पूरी टीम ने है, उन सबों का भी जो है सो बहुत बहुत धन्यवाद। मैं हमारे सभी आमंत्रित अतिथियों को, वैज्ञानिकों को, मीडिया प्रतिनिधियों को, जिन्होंने हमारे इस कार्यक्रम को सफल बनाया, उसके लिए आप सबों का बहुत बहुत दिल से हार्दिक धन्यवाद। और हमेशा याद रखिएगा, संघर्ष सुविधा को जन्म देता है और अंतिम में सुविधा हमें संघर्ष की ओर ले जाता है। तो हमें जो सुविधाएं मिल रही हैं, हम लोग उसके लिए संघर्ष करें और सुविधाओं को जन्म दें। आप सब लोगों को यहाँ आने के लिए, अपना समय देने के लिए बहुत बहुत धन्यवाद सर। थैंक यू वेरी मच।
धन्यवाद महोदय। अब मैं सभी से राष्ट्रगान के लिए यथास्थान खड़े होने का अनुरोध करती हूँ।
जन गण मन अधिनायक जय हे भारत भाग्य विधाता। पंजाब सिंधु गुजरात मराठा द्राविड़ उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तब शुभ नामे जागे तब शुभ आशीष मांगे गाहे तब जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे।
आज के कार्यक्रम से जुड़ने के लिए आप सभी का हार्दिक धन्यवाद। सभी के लिए जलपान की व्यवस्था बाहर की गई है। आप सभी का दिन मंगलमय हो। नमस्कार, जय हिंद।